And do I have to write a report in real time, like, or do I have some time, like, a day or two or whatever? I see. I see. I got it. Perfect. Thank you. Ah, okay. Okay. Yeah. Okay.
Ah, bah Thierry, t'es déjà là.
Hi.
Clara?
Hello.
Hello. Good afternoon.
Hello.
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 I don't know if all these remember I hear.
Hello.
It's okay or not? So just to check. Mathieu Aubry is here. Christian So, Rogetsu, Thierry, Anna, Thomas. Are you here? Thomas?
Yes, I'm here.
Yes, okay. So we can switch off the microphone and we can late.
And the cameras.
And the camera also, yes. And Thierry is the president, so maybe Thierry, you can share right now.
Do you see already my screen?
Yes, perfect.
Yes, it's fine.
Okay.
So good morning, Thomas, and good afternoon, everyone else. So I'm Thierry Château. I'm professor at Clermont-Auvergne University, and it's a big pleasure for me to chair this committee. Let me first introduce the member of the committee by beginning by the reviewers. So Christian Wolf, maybe you can switch on your camera for a couple of seconds. Christian is associate professor at INSA de Lyon and member of Lewis Laboratory. Then Mathieu Aubry. Mathieu Aubry is a research scientist at École des Ponts at Marne-la-Vallée. Then Thomas, sorry for the pronunciation, maybe it's wrong, Thomas Funkhauser is professor of computer science at Princeton. And let's finish by the supervisor. Jose Guerrero is professor at University of Zaragoza. Ana Murillo is associate professor at University of Zaragoza. And Cédric de Monceau, professor at University of Burundi. I would just ask to other people to mute their microphone and camera. And so, Mrs. Clara Fernández, you have 35 minutes to present your thesis works and your contribution, and we will step to the session question after.
Okay, thank you very much. So you say you can see my screen, right? So, well, welcome everybody, and thank you for attending this PhD defense. I would like to especially thank the jury members, so Thierry Château, Christian Wolf, Mathieu Aubry, Thomas Funkhauser, and Ana Murillo, for generously offering their time and accepting being here today remotely. And also to my advisors, José Jesús Guerrero and Cédric de Monceau, for making all of this possible, and to all my collaborators. So, today, I will present the work of 3 very special years that I've titled Endorsing Understanding Using Non-Conventional Cameras. So, some time ago, I discovered this survey that contains a shocking fact, which is that humans, in average, spend almost the 90% of their time in indoor spaces. So, there is actually a real need to understand properly indoor scenarios to improve life quality indoors. And this understanding, however, is not trivial, as there are hundreds of different man-made scenarios which can differ for many reasons. To name a few, we can start with the layout, which can range from very simple, you can imagine a typical bedroom with 4 walls, to highly complex layouts as in museums or supermarkets. To continue, the diversity of objects of interest is very high, many of which appear infrequently. And also, indoor spaces usually contain many instances, generating in the visual scenes clutter and high degree of occlusions, which makes very hard to know the separability of objects and surfaces. Therefore, achieving a complete understanding of indoor scenes will equip the discipline of computer vision with many exciting tools, thus making it more powerful and ubiquitous. So when we talk about indoor scene understanding, we can actually think about the different levels of details that we want to understand. And also, we want to find the most suitable sensor for each specific task. So typically in computer vision, we are given an image coming from a conventional camera like the one on the left. And we aim at creating models that are able to recognize the scene, for example. So is this a living room? Is this a bedroom? Also to estimate the layout. So how many walls are in here? Where is the free space I have? We want to also recognize the objects, so how many objects, where are they located, and also it would be interesting to know the pose and the geometry of these objects. So I want to challenge you to try for a second to answer all these questions just looking at this image with no extra context. And you probably struggle, right? At least I do. So if you think about it, the goal of computer vision is to mimic the human visual perception, which is already a really complicated task. So just for comparison, humans perceive an horizontal field of view of 120 degrees without considering the eyes movement. Otherwise, it's even more, right? And also, human stereo vision makes possible the 3D perception. This implies that the reduced field of view or the lack of depth information in single 2D conventional images crucially limits the goal of developing intelligent systems to match the performance and the robustness of human vision. So we observed that ultra-wide angle lenses can be beneficial, particularly in indoor scenarios for many different tasks, which is not surprising since a field of view of 360 degrees allows to see the whole scene at once, providing a great context to achieve a high-level understanding of the scene. So for example, for space recognition, layout estimation, or object localization. Therefore, during this presentation, we will see how to exploit the full view of the scene offered by 360 images and how to deal with the inherent distortions. On the contrary, when we look at an image of a 3D object, we see only its contours from a specific viewpoint. So if we want to understand the details, the geometry, the shape and pose of the objects, we need to go deeper into its own structure. Therefore, for the case of object shape analysis, we instead prefer to work directly in 3D, where we can use 3D point clouds or 3D meshes, for example. So today, I will cover 3 fundamental tasks in computer vision for indoor scene understanding, which I've divided in 3 levels of abstraction. So the first one is the layout level, where we will talk about the main structure of the rooms, how to recover it. Also, in the scene level, we will be interested in recovering like the objects that are inside the 3D scene. And then in the object level, we want to understand the pose and the shape of the objects per category. So since in the 2 first levels, we will talk a lot about 360 images, before we start diving into the 3 different topics, I want to give an overview about the spherical images and their peculiarities. So one of the main challenges here is that the sphere is not a developable surface, and hence there is no perfect mapping to go from a spherical image to the plane. So according to the Gauss theorem egregium, the Gaussian curvature of a surface is invariant under the local isometries. So since the sphere and a flat plane have different curvatures, these 2 surfaces are not isometric, hence they need to get rid of this. And as you can see at the bottom, there are so many prior projections, planar projections of the sphere. Here I put only a few. And also the waterman is absolutely my favorite. Let's not overcomplicate things and go for the equirectangular projection. So generally, the equirectangular projection is preferred in computer vision as it's equidistant. This is because a rectangular projection maps the meridians and the parallels of the sphere to vertical and horizontal straight lines of constant spacing using the spherical coordinates. This implies that we have a direct relation between each point on the surface of the sphere, represented as the ray coming from the center of the camera, and the corresponding pixel coordinates on the image. And this relation simply depends on the spherical angles and the resolution of the image. The projection, however, is neither equiareal, not conformal, And this inevitably generates some distortions that are more pronounced near the poles, where the areas get stretched horizontally to the entire width of the image. So for example, the entire top edge corresponds to a single point, as does the lower edge. A particularity of these images is that for a straight line in the world, we can see, for example, the red line. There exists a plane that includes the line itself and the camera center. And as you can see, the intersection of the plane and the spherical surface creates an arc segment onto the unit sphere, which is the reason why lines appear as curves in the equirectangular images. So we can model lines in the panorama by the normal vector of the plane where its curve lies in. Additionally, another peculiarity is that whereas in conventional images, parallel lines meet in a single vanishing point, in spherical images, they do in two antipodal vanishing points. So for example, here the red and the blue lines are parallel in the 3D world, and they intersect in these two antipodal vanishing points, right, also in the image. So to finish this overview, I also want to mention that existing methods are not suitable for 360 images. So in case we want to take advantage of previous work, there are two options. The first one is that we can unwrap the spherical image into its rectangular projection and then apply directly the method on the distorted planar image. This will be fast because it runs directly in a single image, but it's accurate because of the domain shift. The second option could be to sample multiple perspective images from the original image, apply the method independently to obtain local results, and then go back to the panorama. This will be more accurate but slower. So now we are ready to start with the room layout, which is the coarsest or the highest level of abstraction of the scene. And this topic is receiving more and more attention thanks to the potential it has for many vision application markets, like virtual or augmented reality, indoor navigation, or even real estate. So what is the room layout exactly? Room layout refers to the main structure of the room, which is represented by the walls, ceiling, and floor. Also, the room layout can be obtained in 2D and in 3D up to a scale. And I say up to a scale because we don't have any depth information. Then we will use a corner representation, meaning that the output of our algorithms are the corners of the room. And also we want to predict the layout so that it's representative of the real shape of the room. And why I'm saying that? So here I show you the two seminal works dealing with this problem using perspective and panoramic images respectively. And as you can see, the problem is quite new compared to others, and especially with panoramic images, it's hardly 5 years since it started, being still unique when I started reading about this problem. And also, previous methods show exceptional results, especially pano context is pretty impressive. I found a common assumption in all these works, which is that rooms have only 4 walls. And whereas with conventional images, it makes sense, right? Because we only see a portion of the scene. I thought, okay, so panoramic images should actually open a new door to overcome this simplification. And this is what initially motivated me to work on this topic. So let me state all the challenges that we want to consider here. So the first one is that we want to infer the 3D structure from a single monocular image, which is one of the holy grails of computer vision. Then we want to deal with the spherical distortions, which not only means about dealing with the distortion itself, but also with this fact that we cannot use previous methods. Then we will need to deal with high degree of scene occlusions and clutter, because remember that we want to abstract the objects and predict the main structure of the room. Then we also want to overcome the 4-wall room simplification, and we want to reduce the computation times with respect to the state of the art. So I want to talk about 2 works in this level. Let's go for the first one. As a first step, we aim at extracting all the visible lines in the panorama and estimate the orientation of the scene. And since we don't have any depth information, we assume that we live in a Manhattan world. This assumption leads the vast majority of works on monocular structure estimation and basically establishes that there exist 3 main orthogonal directions that define the scene, X, Y, Z, and they appear represented with different colors in the image. So first, in order to estimate the lines, we propose a ransack-based algorithm that works directly on the spherical image. So we run a traditional edge detector on the image and then use contiguous elements to sequentially fit lines according to our model of line in the spherical representation. And then once we have the lines detected on the panorama, we can find the main vanishing directions as a consensus set maximization, where the objective is that the maximum number of lines passes through the vanishing points. And since we look for a corner representation of the layout, we can intersect the estimated lines in order to get the candidate corners for the reconstruction. However, in cluttered scenes, it's very difficult to know whether they come from actual wall intersections or from other elements of the scene. And proceeding with all the corners will lead to an intractable number of hypotheses. In order to tackle this problem, we explore an existing deep learning approach that outputs from a single perspective image a probability map encoding the per pixel probability of being part of a structural edge, so the intersections between walls, ceiling, and floor. And we use the second strategy mentioned before to get an output from our rectangular image, which, if you remember, is a bit slow since it requires to divide the image into several perspective images, but at least it gives us a reasonable output. And as you can see, even if the edge map is not sufficient to get directly the structure of the room, as it shows some thick edges and some noise, it provides a good hint about the room structure. So here comes the question, geometry or deep learning? And we propose to combine the strengths of the two worlds by assigning the edge map probabilities to the full set of lines in order to filter them and get only the most informative and accurate ones regarding the structure of the room. This means that all the lines belonging to the black areas in the probability map will be removed. And now, if we intersect this new set of corners, the number of candidate corners that we obtain is vastly reduced, being more meaningful for our reconstruction algorithm. Here I show you some more examples where you can see the huge reduction that we get in the number of corners. And just as a note, we can divide the corners as candidates for floor and ceiling using the horizon line as a divider. And now the challenge is to find the set of corners among these ones that actually represent the layout of the room. One of the biggest challenges is that sometimes some of these room layout corners are hidden in the image, either because of occlusions, like for example, the corner behind this plant, right? Or because of the convexity of the scene in more complex layouts, because it can happen that sometimes one wall hides a part of the room. So this implies that such corners might not be detected in previous steps. So in order to recover the 3D layout of the room, which we represent by the room corners, we propose an algorithm that iteratively generates possible layouts based on 3 assumptions. The first assumption is the Manhattan wall. So we will try to generate consecutive walls perpendicular to each other. Then a second assumption is that the ceiling and the floor are parallel. This means that all the ceiling corners should be on the same plane and right above of the floor ones. And then we will need to assume a camera height, which is trivial, then the number we choose, as the results are going to be up to a scale. And also the proposed algorithm works directly in the 3D Euclidean space. Thanks to the second assumption, we know that ceiling and floor corners share X and Y coordinates. So we can exploit this idea to work directly on a top view of the 3D scene, like in here, reducing the dimensionality of the problem, as we can predict 1/2 of the room corners and then lift the 3D model by estimating the total height of the room. So how does this work? At each iteration, the algorithm samples a small number of corners from the predicted ones, which we show here in yellow and cyan color. And then we try to draw possible Manhattan layouts using perpendicular consecutive walls. So one of the highlights of the method is that we can draw new corners, the green ones in the image and here. And this is what we use to close the room layout according to the Manhattan wall assumption, but it also is especially useful to find hidden corners in the image that were not predicted originally. So here I show you some results, including a comparison with previous methods. And in the diagram, we show how our model with only 10 hypotheses is already able to get over a 90% of accuracy in less than 2 seconds, whereas the compare method after 100 hypotheses only gets around a 60% of accuracy. And additionally, if you look at the 2 images at the bottom, you will see how our model in cyan color is able to faithfully recover the real room structure, whereas the compare method only detects 4 walls, which is the dark blue. Now, let me go to the second method in this layout level. So we note that using traditional methods with 360 images represents a major bottleneck in most recent methods. And the estimated results are not as good as we would desire. And this is not surprising since first we are not using the full context of the image, right? Because we had to split the panorama. And then panoramic images contain scene parts such as the saline or visually less meaningful regions that generally do not appear in conventional images, and then the generalization is sometimes poor. So for this reason, we propose a fully convolutional neural network that works directly on the full panorama and predicts two probability maps, encoding in this case the corners and the edge maps and the edge of the rooms. So we learn them using a single decoder, which benefits the joint learning as both tasks are very related. So we use an encoder-decoder architecture where the encoder is the ResNet 50. We use some skip connections and preliminary predictions. And the problem here is that the datasets with 360 data are not very massive. At least they weren't in that moment. And so it would be ideal if we could use pre-training with conventional images, right? But we have this problem of the distortions. So by that time, there were some proposals to use rectangular kernels instead of square ones in order to learn the panoramic images. But even if they show that this helps, this doesn't solve the problem of the distortions. And not only that, additionally, in 360 images, the left and the right side are the same spot in reality. So if we use a common standard convolution with the corresponding padding on the borders, the networks simply do not understand the continuity of the scene. So for example, if we were detecting imperial soldiers in this image, we will count this guy twice. But actually, as you can see in the bottom, I just copy the image again on the right. It's the same guy. And this will be critical for room corners that appear on the borders, which we observe that sometimes happens with the standard convolutions, and this is not desirable, right? So what we do here is we propose a new type of convolution, which is called equirectangular convolution. So basically what we do here is to propose a kernel that adapts its size and its shape to the equirectangular image distortions. And we define it using the resolution, which is the typical 3x3, and also the angular size, which we can get directly as we know the 360, the full width of the image is 360 degrees. And also then this kernel will be convolved around the sphere using the spherical angles. So imagine that we have a 3x3 kernel like this one, tangent to the surface of the sphere, with its center in contact with the surface. So we can define the kernel by the 9, in this case, rays that go from the camera center to each kernel position. And then in order to wrap the kernel to the sphere surface and convolve the spherical image, we normalize the kernel and then rotate it using the spherical angles. So you can see in both images how the kernel gets more distorted near the poles, whereas in the center is hardly distorted, following the equirectangular projection distortions. First, this means that the learned convolutional filters are deformation invariant by construction. Then we don't need padding anymore, as when the kernel arrives to the border, it knows where its corresponding position on the other side are, right? For example, here, you can see the same kernel in the spherical representation and in the equirectangular representation. And additionally, we can now use pre-trained models in order to get very accurate edge and corner maps. So the last step of our proposal is to get 3D models, the 3D model directly from the corner map without additionally usually expensive hypotheses. So the assumptions now are only two. We will assume the ceiling floor parallelism, but not the Manhattan wall anymore, like the complete assumption, right? Because now we don't force the walls to be perpendicular to each other. And then also we will assume a camera height as before. So we work directly now with the 3D rays whose origin is the sphere center and go through the room corners locations on the spherical representation. So we first intersect the rays corresponding to the floor corners on a common plane at distance h that we are assuming, and then we look for the complementary distance to the ceiling so that the ceiling corners are right on top of the floor corners and the ray equations are satisfied. Sorry. So here I show you some quantitative results. Here we evaluate the room layout, the resulting room layout. So we use 4 different metrics. First, we evaluate the 3D intersection of a union, comparing the ground truth and the predicted 3D model of the room. And then in 2D, we evaluate the corner error using an L2 distance, and also the pixel error which is using a segmentation map of the room that encodes the different surface of the room. And as you can see, our model performs better than previous methods, and especially using equirectangular convolutions. And also, as you can see on the right, our method, since we are avoiding extra expensive pre-processing or post-processing steps, is much faster than previous methods. Now, as an additional remark, when we evaluated the output probability maps using standard and equirectangular convolutions, we observed that the model with standard convolutions was performing worse, but still surprisingly good. And then we realized that all the training images were taken with the camera in the center of the room, which creates a very characteristic pattern of the layout due to the distortions. And then the standard convolutions were somehow overfitting to this pattern. To show this, we carry an experiment where we modify the input images by applying some translations and rotations, reproducing real scenarios where the camera can be in a drone or in a small robot or simply be a handheld camera. And as you can see here, the layout pattern is modified so that when we test with these images, only test, the model with equirectangular convolutions, aware of the distortions, is able to generalize better to camera pose variations compared to the same model using standard convolutions, which makes the proposed convolutions even more powerful. Here, I just want to show you some extra qualitative results. All of them show more than 4 walls for the rooms, so more complex layouts. And as you can see, in general, it works pretty good, except in some failure cases, of course. And then here I show you also some extra results with 3D models. And as a summary, we end up with a model which is very fast, right, because it's end-to-end. Then we are able to use the full context of the image because we are working directly on the panorama. And thanks to the equirectangular convolutions, we are aware of the distortion model. And then our final models represent the actual shapes of the room. So with this, we conclude the layout level. In the scene level, we also bet for 360 images, and we are interested in object localization and segmentation. And then we also explore how to lift the 2D predictions to 3D using as prior the room layout. So again, let me state all the challenges we consider here. So again, we want to infer 3D structure from a single monocular image. We want to deal with spherical image distortions, which in this case is going to be even more meaningful, right? Because we have many different objects. Then again, we have a lack of massive 360 datasets, and then we will have the typical challenges of object detection, right? It's that objects appear in variable size and orientations. They can be occluded, blended with the environment, illumination conditions, etc. So here we propose a similar neural network as the one before. So it's an encoder-decoder with ResNet 50 in the encoder. And again, we use skip connections and joint learning. In this case, what we learn together is object detection, so bounding box detection of the objects, and semantic segmentation of the image. So we will modify the aspect ratios of the bounding box so that it matches better with a ratio of the equirectangular images, and we include equirectangular convolutions as well in here. So here we evaluate the predictions of the neural network, and we evaluate, in the first case, the 2D bounding box predictions per category, and so a 10% improvement over the work over previous works. And this is measured with the average precision. And then if we evaluate the segmentation results, we improve in almost a 20% using the intersection over union with previous method. As you can see also, the model with equirectangular convolutions works better than if we only use standard convolutions. So as we already mentioned, we decided to go one step further and try to lift these 2D predicted objects to 3D. And the idea is that one can make use of some safe assumptions, since objects are not randomly located in the scenes. Objects are fairly constrained to lie on at least one supporting plane, which can be the floor or another object, and aligned usually with the room walls. So if we think about it, this means that the room structure provides strong contextual cues as to where and how objects can be found. So for this reason, in order to lift the objects to 3D, we use the room layout as a prior. And what we have is either a 2D representation of the layout, which can be a segmentation map encoding the ceiling, floor, and the different walls of the room. And also we have the same planes, but in 3D, which are the corners that limit the plane, the normal direction of the plane, and the distance from the plane to the. Additionally, we also make 3 assumptions. The first one is the Manhattan world assumption. We already talked about it, but basically means that there are 3 main orthogonal directions that define the scene. Then we assume no floating objects, and then we assume that objects that are in contact with the room walls are aligned with the scene. So the last assumption sounds a bit restrictive, but it's purely based on observation walls, then it's aligned with them. If the object has a random pose, it's more probable that it's not in touch with the walls, but it's in the middle. So, for example, in this image, as you can see, the bed, the table, the mirrors are aligned with the scene and in touch with the walls. But for example, this small sofa, it's in a random pose and it's not in contact with the walls, right? So we propose this assumption to decide which objects to lift to the 3D, because for those objects that are in the middle of the room, we cannot recover its height, since we don't have any depth information, but only the layout prior. So as a first step, we need to get the instance masks of the objects. To do so, we merge the object localization and semantic segmentation results, which not only allows us to get the separability of the objects, but also to improve some of the masks, as you can see in the green boxes compared to here. And now what we do is we approximate every object mask, as you can see in the top and on the bottom, with lines. To do so, we use all the counterpoints of the object mask and propose a sequential ransack-based approach, similar to the one I mentioned in the layout level, that basically fits 4 straight lines to the mask, as you can see on the top and on the bottom. So then we classify the lines with the main directions of the scene to know the pose of the object, right? Because as we said, only those objects that are aligned, we will consider that are in touch with the walls. So for example, in this case, the blue lines encode the Z direction, and then red and green lights encode the X and Y direction. So then for those objects that are aligned with the walls, we take their interaction with the room planes. And to do so, we computed the intersection between the object mask and the segmentation map of the room, that if you remember encodes the different walls, ceiling, and floor. Then for planar objects that line on one plane, like for example the walls, the mirrors, the paintings, we just backpropagate the bounding box that best fits the instance mask in the corresponding wall in the 3D model. But then for cuboid objects, what we do is we backpropagate the lines that are in contact with the planes, like for example, in this case, this wall and this floor planes. And once we have them in 3D, we can directly get the dimensions of the cuboid object. And then, of course, we can backpropagate the result to the image. So here I show you some qualitative results. And as you can see, there are no objects placed in the middle of the room. One option could be just to assume an average cuboid dimension per object category, but we decided to place only the ones that we can actually compute a more accurate dimension according to the scale of the layout. So with this method, we are able to get representative 3D cuboids of the objects in the scene. And this motivated me to go one step further and try to analyze the 3D shape of the objects in more detail. And this brings us to the last level, which is the object level. So in this work, aiming for a detailed understanding of the object shapes, we want to learn 3D key points from a collection of objects in a category so that they satisfy the following properties. So first of all, they should generalize over different shapes and alignments in a category. We should have one-to-one order correspondences and be semantic consistent. And also they should be representative of the instance and the category itself while preserving symmetry if it exists. And this is very interesting as category-specific key points are a key building block for downstream tasks such as 3D reconstruction, geometric registration, non-rigid structure from motion, or pose estimation. So In contrast to previous methods, the challenges we consider here are the following. So the input shapes in our case are going to be point clouds, and they are not necessarily aligned. Then we have to take into account that 3D objects go through shape variations, either because they are deformable, like the human body, or when we compare two different instances of a category. Then not all objects in a category necessarily have the same semantic parts. For example, this chair has arms, whereas this chair hasn't. And since we are looking for correspondences between instances, this is important. Also, we want to take into account the notion of symmetry. And then, since we don't have any ground truth data, we want to develop this with unsupervised learning. So we propose to solve this problem by modeling shapes with non-rigidity. And the idea is that shapes of a category, even if they go through some variations, they share similarities to a large extent. So we can think that there might exist a deformation function that maps a global shape property that can be a template or some basis shapes to an instance shape of the category. However, modeling such a deformation function is not trivial and may not exist in many cases. In fact, this is what makes dense non-rigid structure of motion so challenging. But on the other hand, one can imagine a deformation function going from a global key points property to the key points of a category instance. We therefore seek for the non-rigidity modeling in the space of key points. So one of the most common approaches of modeling shapes as non-rigid deformation is the low-rank shape prior. The key idea is that a large number of object deformations can be explained by linearly combining a smaller number k of basis shapes at some pose. This means that we can obtain any chair instance shape by linearly combining some shape bases which are common for the whole category chair with some shape coefficients that are specific for that particular instance. Remember that we said that we work in the key points space. So instead of having full shapes, our bases will be sparse key points. And also, since we said that our input shapes are not necessarily aligned, we will also include a rotation per every instance. Well, and this is the mathematical model that we use in our network in order to learn such key points in an unsupervised way. So this is our network architecture, which is trained per object category. And how does this work? So every input shape is an instance of the category and is passed through the nodes branch, which is used only for training and outputs some nodes learned in a pointnet-like fashion. In parallel, we use a multi-layer perceptron in order to predict the instance-specific parameters for our deformation function, which, if you remember, are the rotation and the shape coefficients. And then what happens with the parameters that are common for the category? What we do is to optimize them inside the network as the network weights. These parameters, if you remember, are the basis shapes. And also, in case we want to model symmetry, we can also learn here the normal direction of the reflective plane of symmetry of the category. So once we have all the ingredients for our deformation function, we can compute the linear combination and obtain our category-specific key points. So in order to guide the learning, we use three loss functions. The first one is the chamfer loss, which basically tries to align the nodes and the category-specific key points as you do in ICP. Then the coverage loss compares the total volume between the nodes and the input shape in order to ensure that they are representative enough. And also the inclusivity loss that penalizes key points that go far away from the input shape. As we said, we can add symmetry, right? And in our case, we realize that adding symmetry helps to reduce the dimensionality of the problem and get more meaningful key points. So in this case, it's very common in a large majority of rigid object categories to observe at least one plane of symmetry, right? So we don't assume the plane of symmetry to be known and just decide to say, okay, you have to predict one plane of symmetry, but potentially we could predict more than one. And the idea is that we predict only the half of the basis shapes, we linearly combine them, and then we can use the reflector operator in order to reflect the key points and get the symmetric ones. But what happens with non-rigid objects like the human body? because humans are symmetric, right? We have 2 legs, we have 2 arms, but due to the pose variations, shape instances may not be symmetric. So here we observe that the notion of symmetry still exists in the category deformation space. As for example, we can have one instance with only its right hand up, but it's very probable that there exists another instance with the left hand up, right? So they are symmetric. In order to implement this, what we propose is to model such key points by introducing symmetric bases that can be weighted asymmetrically. And here we can see some evaluations. As you can see on the left, our key points are always predicted in the same geometric and semantic locations and are ordered. The order is represented by the key points color, right? And in the middle, we plot all the key points of the instances of the category. And as you can see, they get neatly clustered, showing some variations that actually capture the variations in shape. And in contrast, a comparing method show a more random clustering, as they do not predict similar key points between instances of the same category. Another peculiarity of this key points is that they are ordered and they are correspondent, right, between different instances. So we actually can use them directly for intra-category registration. So here we perform an experiment where we measure the relative rotation error when we try to align these different instances. And we observe that, of course, when we have higher misalignments in the input, we get higher errors, right? But if we include the notion of symmetry, what we observe is that we have more control over the rotations and we can handle higher misalignments. So here I want to show you some qualitative results. This is using the ModelNet dataset. So here I show you some results in the table. As you can see, they are quite different, but they predict always the same key points, right? The same with the chair category and the same with the beds. I also show you here some examples with the human body and the faces. And this is also really cool. So in this case, what we did was to train the model with CAD chairs and then test the model with real data, right? As you can see, the real data is noisy, has some missing parts, and our model, since it's already aware of the shape of the chair category, it's able to place key points in missing parts representing the actual shape of the object. So with this, we conclude the 3 different levels of abstraction of this thesis. And I would like to finish with some conclusions, contributions, and future work. So in the layout level, the sensor matters. So 360 images are an excellent choice for high-level scene understanding, which is in this case the layout reconstruction. Also, end-to-end approaches are preferred in order to reduce computation times, taking into account the possible applications of this problem. Then equirectangular convolutions are a natural choice to deal with these image distortions. And to finish, it's very important to develop methods that are able to deal with hidden corners in order to recover the real shape of the room. So related to this layout level, we have 3 publications, which were accepted in some computer vision and robotics conferences and journals. And the respective source codes are available in GitHub. And as a highlight here, we are very happy that EquiComps were also added to the official TensorFlow add-ons and were implemented as well in PyTorch by other members of the community. And this is because these kind of convolutions are not only useful for layout or object detection, right, but for every task that involves 360 images. Then in the scene level, again, the sensor matters, right? We also see that 360 images provide a great context in order to predict the objects that appear in the scene. Then equirectangular convolutions have even more impact for the task of object detection, as objects can be at many different locations inside the scene, right? So objects closer to the camera will have greater distortions, and objects around the horizontal line will have less. And additionally, since the distortion depends only on the polar angle, objects that appear orthogonal to the viewpoint will be symmetrically distorted, whereas objects at different poses will not. Therefore, equirectangular convolutions here play an important role since they can learn the object appearance by ignoring the spherical distortion patterns. And then what we learned as well is the layout prior provides a strong spatial contextual cues as to where and how objects can be found. And this work was presented in ICRA 2020, and also the extended dataset is available online. And to finish in the object level, so now we know that learn shapes, shape models is possible with unsupervised learning. And in this case, we use a low-rank prior to model non-rigidity inside the network. Also, our key points are consistent over inter-subject shape variation and intra-subject deformation in a category. And we also learn that symmetry helps to have more control over the rotations and tackle higher misalignment. This work was presented in ECCB 2020, and the code is available in GitHub. So in general, we advanced the state of the art on the 3 presented topics, as well as presented some novel ideas. However, as always, every novel idea or discovery not only raises answers, but also more questions, right? So here I want to finish with some ideas for future work in the 3 different levels. So for example, in the layout level, I think it will be very interesting to exploit the sailing and floor symmetry inside the deep learning model in order to learn more meaningful corners. Also, I think it will be interesting to be able to predict the order of the corners inside the network, because if we want to handle more and more complex layouts, as soon as some parts are occluded, the order is not direct from left to right, right? And also, we worked with equirectangular convolutions, but ideally, we would like to have also some pooling operations, aware of the distortion models, and also regarding the stride, I think it should be better if we could do like a sampling more regular, better discretization of the sphere, because right now we are using computing the kernel. We have some redundancy zones, let's say. Also, in the scene level, we already saw how we can exploit the layout as a prior, but I would like to also explore how to use this 3D shape modeling of the objects to detect objects more accurately in the images. And instead of maybe detecting a 3D bounding box, predict like a skeleton, which is more representative of these shapes, and we can use the key points for that. And then to finish in the object level, so we observed that for rigid objects, it was working very well, but for non-rigid objects, it was kind of more difficult with higher deformations, right? So I would like to explore in here. I think it will be interesting to combine the low-rank prior with other methods like functional maps or cycle consistency. And another idea will be to explore bilinear models that analyze shape and pose variations independently. So thinking in a more longer term, I would like to see all these concepts applied together because I think a very cool application will be to transfer all of these ideas of indoor space information to real estate industry to model like the existing building stock, right? And this line of work still needs a lot of effort, as we need to consistently model the outdoor of the scenario or the indoor parts consistently and get as much details as possible from the structural components, and then find a new data representation that facilitates this image or point cloud to CAD model conversion. So I hope you enjoy the presentation, and now I'm happy to discuss any questions that you may have.
Thank you very much. Thank you for your talk. Very interesting. We now step to the question session and start with the reviewers. Maybe we should start with Christian Wolf.
Okay. Thank you, Mr. President. Monsieur le Président. Thank you, Clara, for this excellent presentation. Very clear.
Hi, Christian. Thank you.
Thank you very much. So yeah, it's a pleasure to see a presentation. It was a pleasure to read your work. It's great work. So many things you did. Let me start with a couple of questions. No, yeah. Let me, before I start with the questions, tell you also that apart from the scientific contributions you did, it was a pleasure to see that you had lots of other contributions. For example, it wasn't mentioned in the presentation, but you You added, you extended a data set, for example, the Zoom 360 data set was extended with additional masks. You put this online. You did mention in your presentation that you have published most of your code, in particular the Equirectangular convolutions, which I enjoyed a lot, and I think they will have a huge impact, actually. So apart from science, I think equations, theory, experiments, your work will have a direct impact on the community, which is very important. Thank you also to the team of supervisors for having invited me to review this work. So I will ask a couple of questions, and my favorite part of the work, I mean, favorite part, there are lots of great things, but what I really enjoyed here are these equirectangular convolutions, nicely implemented through deformable convolutions in PyTorch, really nicely done. So my question here is not so much on details. I think this was pretty clear how this is done. Normally in a session, you don't start immediately with Outlook questions, but here I would like to start on Outlook questions. Are you aware of the couple of papers which came out recently which applied transformers on pixel level?
Do you know the title?
They're not even yet accepted, but they had this is the reason why this is more an Outlook question. So the title is 16 by 16 pixel patches something. So basically I'll tell you what it is.
Okay,
people,
yeah,
so this is it's a paper, it's an anonymous open review, iClear submission, but we know who it is because they also put the paper on archive. So basically what they did, instead of its image object detection pixel level, and what they basically did is, instead of using convolutions, they created positional encodings associated to each pixel, and then use transformers for the subsequent layers of the neural network, which basically means that you don't have any prior anymore on neighborhood, because convolutions by definition work on neighborhoods, right? The convolution is a mask you put on a neighborhood. And in a transformer, each pixel can be combined to any other pixel. So a certain pixel can attend to neighborhoods or to longer or to mid-range. It can do what it wants. And so the network learns how to combine these equivariant, how to combine these pixels, and learns, for example, to, in some layers, look around in a neighborhood, and in some layers, go further away. So why do I mention this now? My question is, wouldn't it be easier right now to check whether we can replace equirectangular convolutions by this kind of technique, transformers, where we create positional encodings with respect to spherical geometry, and then the transformer network learns to do equirectangular convolutions?
Okay, because in this case, they were using these transformer convolutions for 360 images, or for
no,
or
normal ones.
Normal ones. Okay, so I guess it's application dependent, let's say. It learns how to transform the network depending on the task they are learning, or?
It learns how it's layer specific and it's head specific, right? So I don't know if you're aware of how transformers work, but so they have different heads, and each layer in its head learns its own strategy of attention. So there are other papers which have shown that in the early layers, the networks concentrate on convolutional like near attention. So each pixel attends to nearer pixels, and in higher levels, layers, attention is further away and takes into account context, right?
Yeah. So, I mean, I'm not aware of these words, so I don't know exactly how they are implemented and how they work. But for 360 images, I mean, I think, of course, if this helps for conventional images, why not with equirectangular ones, right? So my only, I don't know, I'm only skeptical to know like how they will take into account the distortions in there, because if they don't take into account like neighborhoods, I don't know. I mean, ideally for rectangular convolutions, what you will need to take care is about the continuity, which I think is very important, because we observed that in many models, like when you rotate the camera also in this direction and you have objects in the borders or the corners, if you don't take into account it's a problem. But then if they can just choose which pixels they take into account together, you don't need to maybe take into account the distortion, right? Because you can also avoid this redundancy of pixels, for example. But I think they should take into account this thing of the continuity. That will be very important. I don't know if I answered your questions.
Normally, there shouldn't be any distortions because the advantage of this thing is that there is no grid, and you just assign each pixel a position, right? So in your case, you could use spherical coordinates, not pixels. There would be no projection into rectangular image anymore. So
okay, I see what you mean.
There is no.
Okay, so you don't need to go to the planar domain.
No, exactly.
Okay.
Because transformers are permutation invariant. They work on sets, right? So the image
like
would
with
be a set
3-point clouds, or I see.
Exactly.
Okay. Yeah, no, okay. That's super nice. Okay, I will read those works. I think it's very interesting.
Because what I also found nice is that you did pre-training on classical images and transferred this to omnidirectional images, and here as well. Well, I will not go into the details. Okay. Second thing, one of the things I was interested in. So you provided experimental results, and you compared this classical convolutions to the equirectangular convolutions, and they were global numbers. So global over the full image. My question is, did you check where you got the gains? Did you get the gains in the corners of the images where the distortions were higher, or were the distributed over the image? Did you check this a little bit?
Okay, so we didn't study actually this thing that you say, and it's very interesting. But I guess, I mean, my guess is that in the middle of the image, you have basically no distortions, right? Because the distortions are more pronounced on the top and in the bottom of the image. So the thing is that we can get higher benefit as soon as the layout or the objects are located like close to these areas, because they get like very, very distorted. And in those cases, I guess, is where you have the best advantages. Instead, that's why also I was comparing like the layout with the objects, because the layout usually is always in the same position. So you get distortions, but it's more or less the same all the time. But with objects, if the object is closer to the camera, or closer to one of these extremes of the image, they will be highly distorted, whereas in the middle of the image, they have no distortions. So standard convolutions actually see them like really, really different, right? Instead, if we have rectangular convolutions aware of the distortion model, they don't get this problem of the higher distortions between the same objects of a category, right? So I guess that's my guess when they are in
It's my guess as well. It's my guess as well, but it might be necessary to check that, because for the convolutions, there is a difference. So we talk about distortions, right? Because we have some intuition what is right and what shouldn't be right. But another way to see it is that what you call distortions is the normal case. And is happening in the middle is different, right? Because the convolutions just need to learn some kind of processing, and you do error back propagation. So what could happen is that the general case, which is learned by convolutions, is the border case, and the error happens in the middle. It might be the other way around. I don't think this is what is the case, right? But I think it might be necessary to check this.
Yeah.
Since it's learning based, right?
Yeah, because it could be that it learns then the distorted objects, and then when it sees a normal object, it gets right. Yeah, it's true. Exactly. So it's interesting, yeah.
In your future work, you talked about exploitation of symmetry in deep learning models on this part here, on this level of abstraction. So my question, what did you have in mind? So did you mean like inductive bias in neural networks, structure of neural networks?
So you mean in the symmetry of saline and floor symmetry I mentioned here?
Yes. Exactly.
So here the thing is that we know what I said before, that the saline and the floor planes are symmetric, right? So you could actually, so in the case, for example, in the object level, we were using symmetry to predict more meaningful key points. And in that case, we just were predicting the normal of the plane of symmetry and then reflecting it directly. In the case of the layout, it's not a direct reflection because it will depend on the position of the camera. So you will need as well the ratio, like the difference of the distance from the camera to the ceiling and to the floor. And then applying this ratio, you could actually do this reflection according to the horizon line and get the other corners. And I say this because of two reasons. So sometimes what we observed is that there are so many occlusions overall in the bottom parts of the scenes, right? Because it's where we have like all the sofas, plants, all the objects. So actually we could rely more on the ceiling corners and then reflect them. That's also why in the first model we were using this method to include new corners because sometimes they are not detected. So if we could only detect the half and trust very well in them and reflect them, we could actually achieve, we will predict less number of parameters, right? And then we will have more control, more geometric control inside the network for achieving a more meaningful prediction of the corners. So my idea will be to try to somehow include not only like a loss function to supervise the learning with some corner maps, right? But include more a geometric reasoning inside the network regarding the symmetry in the 3D Euclidean space.
That's a really exciting idea. The devil might be in the details though, right? Because if you do it right, then the structure of the network, so the inductive bias, satisfies symmetry, and the symmetry has hyperparameters, right? So you need, for example, the room height. So either you first detect the room height and then you construct your network to reflect the symmetry, or the room height is an additional parameter in the network, but on which the structure of the network depends, right? So the devil might be in the details.
Yeah, you could actually try to predict as well this ratio between the distance from the camera to the ceiling and to the floor as like unsupervised, I would say. And when you, I don't know, inside the model, inside the network, like when you check with the loss function, let's say, you could actually reflect these corners and check the consistency with some aspect ratios and also try to penalize so that you can find the correct aspect ratio of ceiling and floor distances. I mean, I'm not sure we should try this, right? But I think it's a good direction.
Okay. I'll need to speed up because I shouldn't take so much time, but yeah, so many things I would like to ask. Yeah, a very high level question. I don't know if you're aware of Tesla's work. So how Tesla does autonomous driving, they have 8 cameras, 8 different directions. Very high level, very open questions. Would you recommend omnidirectional vision to them? What's the difference between having a rig with 8 cameras, planar cameras, normal cameras, versus omnidirectional? So you have lots of. I never worked on omnidirectional vision, so that's the reason I asked it. Would you recommend to somebody like me who never worked on it omnidirectional vision compared to multi-view geometry?
I mean, with multi-view geometry, I guess if they are pointing in all the directions, they also have 360 degrees of vision. And probably with multi-view, they can also get depth information, I guess, right? So, I mean, I guess for me, 360 vision is super important. And in autonomous driving, it's also very important because sometimes they only focus on the parts they have in front of them, right? But actually, in order to predict some movements, it's very important to know also what is happening behind you. But I don't know, I mean, if it will be, for me, ideal to have like stereo 360 images, which probably is what they get with this multi-view of the cameras. So I think it's not that important how you get the information, how you get the 360 image, but the important thing is that you have this 360 field of view.
So how about equirectangular omnidirectional stereo vision? Was this discussed in the project? Why wouldn't, what was the reason of not doing it?
No, we didn't try anything with this, but I mean, of course, if you can, in this case, the challenge was like 3D structure from monocular images. And also was based on the data sets that were available before, because right now 360 image is exploited, right? And there are so many virtual data sets and information over there. But in that moment, we had only monocular vision. But I think that, of course, if you have access to depth information, it's better. Because because in our case, we were predicting the layout only up to one scale, right? But if you have depth information, you can actually give the real scale to that prediction.
Okay. I think I will ask one more question, so I need to choose my level of abstraction, and I will go into the scene level. I have less questions for the key points level. On the scene level, one nice remark. When you talked about back projecting lines to walls, you used the term back propagation. So my remark is only that's probably the generation of students growing up with deep learning, which now calls back propagation every geometrical projection. But this is just a remark. This is not
okay.
So my question is, do you think there could be any learning-based method for the integration of the layout? Because your way of doing it is very based on geometry, which is not a bad thing. But might it be more powerful? And I don't have any clear idea on this. This is really an open question. Could you use the room layout as a prior in the sense of learning? Could you do this based on learning?
So we have right now a new student working on that, and the idea is to include the prediction of the layout inside the model. We are testing two different things. One idea, we already thought about it last time, but then we are trying it now. So the idea is that you could use it as a prior, so include it maybe as an additional challenge, channel on the image in the input. I don't know if with one of these edge maps or corner maps, or try to actually predict the layout at the same time that you predict the objects. Because we observe, I mean, it's not always the case that with multi-tasking you can actually get better predictions. But for example, we observe that predicting at the same time corners and edges helps, and also predicting at the same time detection and semantic segmentation helps. So the idea is to see that also helps in mixing these two tasks because they are actually related, right? So that's one of the things that we want to try.
Okay, thank you. I have no more questions. I'll just have a couple of remarks on the key point level work, so the object level work you did, which is really, really great. Well, I'm waiting to see the application on downstream tasks. I mean, you did tons of ablation studies on repeatability, etc., etc. I like the symmetry prior. And I was also a little bit surprised to see still that in 2020 we can still have incredible performance out of PointNet-like architectures, right? So architectures which take individual points and put them through MLPs and sum them up, which is not your contribution. I mean, what you did around PointNet is great, but well, now let's ask this question: Do you think anything can be done to replace at one point PointNet by something else?
I mean, in our case, in fact, what we observed is that our model works without this branch that uses PointNet-like learning. So actually, it works without it. The thing is that PointNet-like architectures also like somehow, I don't know, learn in a hierarchical way because they do this clustering and then they learn in this cluster-to-point interpolation, so they can locally aggregate some information. And we observe that this helps for training. But in our case, that we were using unsupervised learning using this non-rigidity modeling, that was enough. So I think that if you can somehow transfer these input shapes with very simple like multi-layer perceptrons that we were using in here and some additional parameters inside the network, you can actually achieve like already very good results. So of course, I think there can be huge improvements in how we learn from 3D data. It's very complicated task because you only have an unordered set of points, right? It's not like in the image domain that everything is nice and with color information and everything. But I think that also like this kind of unsupervised learning is very powerful to learn on point clouds.
Okay, so what I gathered is that the clustering part is a crucial step, right? I mean, removing it would be not a good idea.
No, the contrary. So we this clustering, this nodes branch, which is the one that is PointNet-like structure, the model works without this branch.
Oh, right. Okay.
Yeah, it works without this branch, and we only use it in training because we observe that it helps. The thing is that since it's unsupervised and we don't have any ground truth data, we cannot validate exactly. It was more based on observations, right? We guess, okay, if we add this, the results look nicer, but it works without it.
Okay.
Yeah. Yep.
Okay. Thank you. I don't have any questions anymore. Thank you very much for your work.
Thanks to you.
Thank you.
Bye.
Thank you, Christian. Let's go to the second reviewer, Mathieu Aubry.
Hello. So just like Christian, I will start by congratulating you. I think it's a very broad set of work. So I think that probably to me that's the most impressive thing, the diversity of the things you worked on. And I think even more impressive than the diversity of the things you worked on is the diversity of things you actually managed to present in this presentation. So I didn't expect you to present the full thesis in 30 minutes. And so to me, at least it was very clear. So I think that was very nice.
Thank you.
So just as Christian, I also think the equirectangular convolution is probably the main the highlight of the thesis, but I will try to focus more on the 3D part for the questions. But maybe first a question about the relationship between the two parts, or the first two parts and the last part. So why didn't you try, or did you try to predict depth from your omnidirectional images?
I think it never was in my plans to predict depth. I mean, I had other friends already working on depth estimation, so I enjoy more like this part of like depth from monocular images. And then when I moved to point clouds, it was, well, I also changed, right? I did this intrusive in ETH Zurich, and I already arrived wanting to work with objects because I was already working with objects in 360 images. So I wanted to learn more on those. And we started actually working a little bit with object detection in 3D, but purely like detection, like 3D bounding box, but with point clouds. And then at the end, we discovered this more interesting and exciting idea, and we started working on that. But yeah, my answer is that I never thought about doing depth estimation.
So do you think it will be possible to do it from omnidirectional images, or there will be some issue?
I mean, I think you can, right? I mean, you mean from monocular 360 images to get depth, or?
Yes,
so
just like single view depth prediction.
Yeah, I mean, if you have enough data, right, you can always do supervised learning if you have the correct data set. And also, I don't know, yes, I mean, why not? I think nowadays with deep learning, it's like everything is possible. But honestly, I would like to move more to unsupervised learning now that I work with this in the last work. So my focus from now on will be like to direct more, to do this unsupervised learning and not to try to predict using labels. I mean, or at least with with semi-supervised models. But I mean,
Yes, tried it. So do you know if there are data sets or if people have tried to actually?
Yeah, right now there are data sets. There are virtual data sets where they get the depth information without problems, and they have also these normal directions, normal estimations per pixel. So right now, in the last year, I've seen a huge amount of data sets coming out with 360 images.
And so I guess they are using this Equiconv as well, or it helps as well, or do you know?
I don't know exactly which ones of the new models. I mean, I received some emails, right, asking, we have the code available, but I don't know if they already tried with depth prediction. I should ask.
Yeah. So then maybe let's move to this 3D key point work. So one thing so how did you decide for the number of key points for a given model?
Yeah, yes. So the thing is that we don't decide the exact number of key points that the shape should have, right? So for example, in the paper or in the thesis, you will see that some objects have 10 key points that best represent the shape, others have 6, 8. So what we do is actually decide one number at the beginning, right? Which is the one that we use, for example, from this sampling on the one we want to include for the basis steps. And we tried, I think, from 10 to 30 or to even 60. I mean, we tried this range because we still wanted to have sparse key points, but we tried with different numbers. And what we observed is that it was quite robust, because always what you get is like some clusters. And in fact, what we are doing then to get the final number of key points is do some kind of non-maximal suppression and get the center of the clusters, basically. So like this is by seeing which clusters are generated, you can see the number of key points that actually define the shape. Of course, you could also like try to play a little bit with the hyper parameters of the loss functions, for example, as well, like how you weight more or less one of the loss functions to get different clusters. But we observed that from this range, like from 10 to 50 key points, you will always get more or less the same clusterings. Is this clear?
Okay. Yes, more or less. But so, for example, you also have quantitative results in your paper. So how so you could evaluate the same metrics for more key points or less key points. So does it continue? So this metric basically don't change with the number of key points?
So for the experiments, I think we fixed, and we were always like using for, I think it was 20 key points or 15 key points in the input. And then we were evaluating with the final result after the non-maximal suppression. So if we get the clusterings like 10 key points, we were evaluating with these 10 key points, for example. But we use for all the models the same initial possible key points and then evaluate the results with the final result.
Okay. And so I understand your initial motivation was to get key points, but is there actually anything preventing your model from learning something similar, but with dense points? So learning a dense reconstruction with a linear basis of points.
So I guess, well, my guess is that if you could increase the number of key points, you will have, of course, a denser prediction. But still, I mean, I think I tried in a couple of experiments, but it's very nice because you still avoid these semantic parts that are not common for the category, right? For example, the chairs that has arms, others hasn't. So the thing is that even if you increase the number of key points, you avoid these parts. So if you want to use this method for full, like to dense reconstruction, you will have the problem that you will miss those parts. But still, like for intra-category registration and these kind of things, it will be possible with denser key points. But the idea was more like to check like which is the most common basis between all of these instances of the category.
Okay, thanks. And so another thing on this is that you presented qualitatively some results on humans. Did you actually try to evaluate the correspondences? Because for humans, you have ground truth correspondences, which you don't have for airplanes or things like that.
No, we didn't try to evaluate this because the thing is that these key points that we predict, they are not part of the original input, of the original points of the input shape, right? Because they are computed with this mathematical modeling. So we somehow ensure that these key points lie on the input shape and they don't go far away, but they are not a real point of the input shape.
You could take the nearest neighbor on the input shape.
Yeah.
Right?
So yeah, but that's a good point. We didn't try that. But yeah, it's true because we were using the Faust dataset and they usually have these clean models where they have like one-to-one correspondences between all the points. Yeah.
Well, they also have scans, which are not clean. So they are real correspondences, but you don't, them are not so clean. I think that will be nice because that will give how it works also for this deformable shape, which are, I think, even more impressive than the rigid shape. So it's good to have key points on a plane.
Sure.
And the symmetry is also much more interesting. So I think it would be really worth evaluating on Faust, for example. So that would be, okay, and so then you mentioned that these key points are useful for a lot of downstream tasks. So what would that be exactly for your key points? Because I have a hard time imagining what they would actually be useful for. So it seems, so could you use them for example, dense reconstruction or for geometry, for example, single view reconstruction or for correspondences? Or so they seem to have nice property, but it's not so clear to me. It's few key points at the end. So you use them for.
For example, saw an experiment where we do this intra-category registration, right? So I think that one is clear. Also, for example, when we do this testing with real data, I think it's also cool because you can like somehow detect even some parts that are missing in the original data because of the noise of the sensor or whatever. We also did an experiment in semantic labeling transfer, I think. And I don't know, for example, also for localization, right? If you want to localize the objects, the chairs, for example, in a scene, and you know the key points that actually identify this kind of category, you could use them for identification. And also for generation of new chairs or tables or whatever. I don't know. I think it's true that I mean,
for generation, it's not so clear to me because so I don't think you can actually get the full shape back from your key points, or can you?
The full shape, probably not. But one of the things I would like to explore in images is that you can actually use create somehow skeletons from these key points, right? Because there are other works that use key point prediction to generate these skeletons. And if you are able to get these skeletons, you already have somehow like the shape of the most basic shape. And then from that, you could do this generation. Of course, with the limitation of these missing parts that I was saying.
Okay, thanks a lot. Okay, I think that covers most of what I wanted. Yes, okay. So maybe a much more open question. So you said what you are interested in now is really using unsupervised learning. So what would you like to do with that?
I don't know. I mean, right now I don't have. So the thing is that I would like to somehow merge all of these works, right? And if I could go back, for example, I don't know, with the layout or everything, as I was saying already, with this thing of the exploiting symmetry with the corners, I will try to include more geometry in the model so that we can avoid somehow this bias that we have with the labeling of the humans, right? Because, for example, in the layout case, we are trusting in these corners, but actually, if the network is not able to find the corner behind the plant, probably the human that was labeling this plant doesn't know where is exactly this corner, right? So in this case, I think it will be interesting to include this Manhattan world assumption inside the network so that you can actually do it in a semi-supervised or unsupervised way. Like include all these notions of geometry that we were doing as pre-processing or post-processing sometimes, try to include them inside the network in order to avoid this human bias.
Okay. Okay, thank you.
Thank you.
Thank you. We go now to examiner, Thomas Fuhunser.
Hello.
Yes, we hear you.
So yeah, I'd like to also start by saying I think you did an excellent job in your presentation. It was all very, very clear and very impressive.
Thank you, Thomas.
Sure. So I guess I'll start with some of the key point stuff. I think it's very cool. So forgive me if I missed it, but the symmetry, do you assume that all objects have symmetry? And so like then what happens if you have an L-shaped couch, for example, or things like that? And I guess that relates to some of the things you said about, so this is what you've got here is a little bit different, which is that you're assuming that there's a symmetry, but with asymmetric weighting of the basis functions, but that's not going to cover something like an L-shaped couch or something like that, right? Mm-hmm. So is it, do you do experiments with shapes that are not either symmetric shapes that are articulated or were symmetric in the first place? So we observe that in general, this is satisfied, but it's true that, for example, in some specific shapes that had these asymmetries, it was not working perfect, right? In those cases, if you don't include symmetry, it's able to detect better the key points, but it's true that the thing is that it's able to learn this symmetric space anyway, because maybe it's 3 instances or 5 instances out of many of them. Mm-hmm.
but for those particular cases, it will fail. You will see like the key points are maybe, yeah, a bit more like maybe outside a little bit of the shape or things like that. It's true. Yeah, we should, handle this, take this into account, true.
Sure. And then that, I guess, relates a little bit to the extra and missing parts and the partial shapes that you get from depth scans. So let's talk about the partial shapes you get from depth scans. So you have some sort of prior. So first of all your shapes are not aligned. Is that correct? So you have to predict the rotation as well?
Yeah.
But the rotation is into some canonical domain, and the key points live within that canonical coordinate system. Is that correct? So there's a very strong prior on what the average position for a key point is.
Yeah, so the thing is that when we say that our input shapes are aligned, we don't, when we test, we don't allow, I think here I was showing, no, sorry. Here, we don't allow like a 360 degrees of freedom on rotation. I mean, it's very, very complicated to learn these rotations without any supervision. So we tested like with smaller, and every time giving more rotations. But yeah, you are right. I mean, we tried like giving total freedom and then it was crazy. Yeah.
I got it. I see. So when you have the partial shapes, it can kind of take advantage of like the very strong prior on this is where I expect the key point for the bottom of the right front leg to be of the chair. I see. Okay. And
yeah, the thing is that if we would train directly with these kind of shapes, it will be tricky because in training, in fact, what it's doing is to avoid these non-representative parts, like the arms of the chairs. So if you train with data that has missing parts already, it's kind of complicated. But the good thing is that it's able to generalize from CAD models to real data, because since it's always predicting the same number of key points and in same geometrical locations, right? It's able to then locate key points in the missing parts here.
Right. Cool. It's just as a suggestion. I know that you're not going to go back and revisit this, but if you had added an extra parameter, which is basically a weight or like, a confidence that I believe this key point is present for each key point in your prediction, and then added that to your loss, maybe with some sort of regularizer that says that not all the weights can be 0, then I think that you could have handled the L-shaped couches and the partial depth scans and all that more robustly. And anyway, just as a suggestion for another time.
Thank you.
Yeah.
Very interesting. Yeah.
Maybe
I'll revisit it.
Yeah. Cool. And then with regards to the key point stuff, there's other people who predict key points, maybe with different supervision and stuff like that. Like, so there's key point net, for example, and things like that. And so that's more of a multi-view supervision. Can you talk a little bit about the differences between your key point work and the others? Is it just the kind of supervision you have, or are there other kind of critical differences?
Yeah, for example, here, the baseline that we are using, it's called USIP. I don't know if you're familiar with this work, but it's pretty impressive. They are predicting key points directly in 3D data, and they are also unsupervised. So the thing is that what they do is they use a CMS network. So they actually input the same shape twice, but they apply a rotation to one of them. So then they predict key points. They align again the shapes because they know the input rotation that they use. And then they penalize the key points so that they are the same. So the thing is that they are able to predict some key points that are robust against rigid transformations, let's say. So they are not getting the same key points in different instances of the category as we show here, but they are robust against rotations. And the thing is that a strong thing that they use there is to assume that the input shapes are aligned so that they can actually use these rotations to supervise with the rotation the key points. And in our case, we are only using one input shape, and then all the supervision comes from this non-rigidity modeling.
Cool. That's helpful. Okay. And so then if you were to pull your whole thesis together, you had one more thing to do. maybe it would be to use key point detection or prediction as part of a scene understanding thing. So I have an observation of a scene in a panoramic image, predict the key points of the chairs and things like that. So what is the challenge to that? What would be the hard part of that?
I mean, I guess there the challenging part. Well, first, I think you will need to have some supervision in 2D for the key points, but the good thing will be to supervise it somehow with these 3D key points. I think the most difficult part is to actually get with these deformations and everything, how to project this 3D to the 2D and find the correct pose of the object.
I see. So you have your object detector, and so presumably you could use that to cut out objects, and then the problem becomes very similar to your unsupervised key point detector within the objects. But you think that will be too difficult because the object detector is not perfect and so on and so forth, or?
So I think you could use, for example, well, if you don't have any ground truth data, for example, for the key points, you could use maybe this bounding box location to somehow limit the area where you want to predict these key points and then lift them to so that and see if it matches with the 3D model. I'm trying to predict, of course, this rotation and everything inside the network. So I don't know, I think it could help to do more like a semi-supervised model if you have these 3D models that you learn in another way. But I'm still not sure how to implement this.
Okay, for whatever it's worth, there is a data set, Scan to CAD, that has ScanNet scans with objects located, and their objects are located based on their key points. So so that would be a project you could try if you decided you want to go back to that. Okay, so then I'm switching over to like the layout estimation stuff and probably even the object detection. So in both of those projects, there's a kind of feature learning aspect to them, like to detect corners, for example. And then there's a combinatorial search aspect to them, which is like make a 3D layout, make a layout out of the corners. And your methods seem to focus on the feature detection part of it, like trying to build an end-to-end network, which then forces you into simplifying assumptions with regards to the layout. For example, that the corners can be ordered and things like that.
Yeah.
So, and then the same's true for the object detector. So like, for example, the thing you're comparing to panel context does this holistic scene understanding where they make proposals of entire scenes and then score those. So I guess it's a high level question, which is the hard part of the problem the feature extraction and the kind of the low level corner detection, or is the hard part of the problem the combinatorial understanding of how they go together into a layout? And was the choice a good one to focus on the end-to-end, but simplifying assumptions on the combinatorial part of it? Does that make sense as a question?
Yeah, so I think one of the cool things of panel context was that they were predicting at the same time the layout and the objects inside. Well, it was not based on deep learning, right? But they were somehow adjusting it so that, okay, this object has to be inside the network, right? So it cannot be like the wall passes in the middle of the object. So I think it would be nice to try to learn all of these combinations, and this is the challenging part, right? Because it's true that it's easier probably to only learn objects and only learn the corners of the room layout, but it will be more interesting to check all of these consistencies between them and the space, if it makes sense inside the network altogether. And I think, yeah, this is the most challenging part, actually.
Okay, so, and a related question. So your methods, I would call bottom up, which is that you're kind of running feature extractors for corners and lines and things like that, and then trying to assemble them into higher level structures. So would it be possible? I mean, there are people who also argue for top-down approaches, where you make proposals for things and then you score them. I mean, that's kind of related to what I asked about panel context before, but Let me ask a specific question. So Yasu Furukawa argues for a top-down approach to layout estimation, where you predict areas first rather than corners, because they're just more robust to detect the higher level structures rather than the lower level things which might be occluded and so on and so forth. So can you talk about the trade-offs of just detecting lower level things like corners versus higher level things like areas? It's a question, Claire. I mean, so you detected lines and corners, but you could have also just said this whole area is a wall.
Yeah,
and,
so more
and
like
then built down to
semantic
figure out where the
segmentation.
corners are. Yeah, something.
Yeah.
Or yeah.
Yeah, so there are actually models that what they do is try to predict a semantic segmentation map of the room where they encode like the different surfaces, right? The different walls, the ceiling and the floor. And I think that's cool, but I'm not sure how they accurate are like to detect actually then, because then the layout, when you have to actually create it in 3D, right? You need these joints to know exactly what is the 3D model. So I don't know if what happens or how they solve when this line that separates the different walls, how clear or accurate it is. So I think, of course, this helps. And in fact, I didn't talk about it, but in our first method, the way we were evaluating this layout hypothesis that we were doing was with a normal map of the room. So we were converting our hypothesis into a segmentation map of the room and then evaluating it using a normal map so that we could check actually, okay, this wall makes sense according to this normal map, etc. So I think it actually gives a really good prior, or it helps to understand the room. But I think at the end, what you really need is this structural element, which of course is more difficult to get because of occlusions and these things. But I think there is when you can get like the accurate structural component to get the 3D model of the room.
Mm-hmm. Okay, cool. I have one more short question. So with the equirectangular convolutions, presumably there's a speed hit to running them.
Yeah.
So I've actually used them in one of my projects, and I think it was 6 times slower in our, in the application we were using from Federico Tambari's group. And there was a improvement in performance, like accuracy, but not a huge performance gain. So, I guess you've got it right here. Oh, okay, perfect.
Yeah.
Well, so do you have a performance hit? And then did you try your methods with your standard convolutions? And there's a little bit of an performance improvement. Exactly. Okay,
yeah.
Great.
Yeah. So the thing is that I think it's more related to the implementation thing, right? So what we did to implement these rectangular convolutions was to use the deformable convolutions. I don't know if you are aware of it. They basically add some offsets to the regular kernel positions, but they learn these offsets online according to the task they want to perform. And in our case, what we were doing is to fix these offsets according to the equirectangular distortions, right? So we were actually somehow using this implementation, and probably right now the implementations that people are doing in PyTorch and these things are to improve this speed. So, and they also, as I said, they did a special version that they include in TensorFlow add-ons, so you can now easily use it from them, and I guess it will be like more efficient. So that was the only drawback of these rectangular convolutions, the time.
Okay, great. I'm all done. Thank you very much. Nice job.
Thank you.
Thank you. I will now ask some question before giving to the supervisor. First, I would like to thank you because I joined the other member of the committee. Your talk is very, very impressive and very well illustrated, and just talk like Christian, so many things. Yes, and I think that there are many things that can be used to make some extension or for other fields. So it's very impressive for me. Just regarding to the last question, I think also that GPU is designed to work with classical convolutions, and I don't think that there is a very good implementation or not. But maybe if this kind of kernels is widely used in deep neural networks, people like NVIDIA will try to think of a specific implementation of such operations.
That would be awesome.
Okay. Yes, to begin, a general question. I don't have many questions because many ones have been already asked by the committee. General question, you assume a Manhattan world. This is true indoor, but this is also true for outdoor urban scene. Do you think that we can use your work for outdoor images?
So depending. So for example, if it's outdoor, but we are talking about man-made scenarios, for example, I don't know, a tennis court or something like this, you could, because actually what we are doing is to recover the layout of a scene, right? So if you are outdoors, the layout will be more complicated because here what we are looking is for a closed layout, taking into account that we have a 360 image. So outdoors, you don't have a closed layout, right? It's more kind of open. So of course it could be extended, but right now, how is it implemented? I think it will work for every man-made scenario, even if it's outdoors, but not for the street, a normal street.
Yeah,
but you could extend
my question was more for layout for autonomous vehicle, for example, with the road, with all these things. But okay. We talk about the processing time. Yes, just regarding to the first question of Christian dealing about transformers and positional encoding, I know this is very recent works in community, but it's very interesting. But what I was thinking is that positional encoding could be a good alternative to your problem. Because it can be seen like an additional layer or two additional layers on which you can encode the spherical coordinates, maybe. And with such informations, I think that the network is able to learn this and maybe have good results also. What do you think about this?
Yeah, I mean, I totally agree. The thing is that I didn't know these new works, but right now that you are like Christian and you are mentioning this, I will of course.
In fact, positional encoding is not very new work because it's related to a paper I think which is called ChordConv that has been published in I don't know 2017 I think or something like that.
Okay. So yeah, I was not aware of this direction. But I will definitely look into it. Thanks for the suggestion.
Okay, and just maybe a question also on your slide 24. It's when you predict a corner maps. I was wondering if you could predict some other thing that the corner map and maybe try to classify some corners according to categories. You talk about ordering corners in your conclusion.
So the thing is that, for example, there is this work which is based on conventional images, which is called RoomNet. And what they do is actually they predict one corner map per corner. So let's say you have the same resolution, you predict a map with the same resolution of the input image, but one single map per every corner, and then they classify also these corners. So they have, I think, 10 possible classes where it's like top corner, down corner, but in this case that we have the full image, this classification will be huge, right? And also if you have to predict one equirectangular image per corner, I think it will be, I mean, one of the things that we say that, okay, our model is fast is because we are actually avoiding this kind of extra predictions. And like predicting everything in a single map also helps to the understanding of the context, right? Yeah. So I think in this case, it will be easier to try to predict this corner, the order directly, rather than trying to classify each corner to which category, and also because it will imply that you will need to separate the corners in different maps, because right now what you have is a probability map. You don't have a concept of separate corners till you post-process, till you get the maximum of each heat map, right? Right. Okay. Okay, thank you. It was my last questions. Now, maybe your supervisor. I don't know, maybe we can start with Anna. Yeah, I wanted to mention that Anna is not one of my supervisors. She was actually also a vocal of the
Sorry, so maybe
jury.
sorry, so Anna.
Hi. Hi, Johan. No problem. So actually, I've been lucky to be in the same lab than you. So I'm not your supervisor, but I would have loved to supervise a student like you. You have done a really great work. So just first of all, congratulations to you and also to your supervisors, okay, and your collaborators, because you have really super interesting results. And well, in any case, for the sake of time, I think we are getting a bit short with time. So yeah, basically congratulate you and highlight. I think Christian already mentioned that your work has a lot of additional contributions, not just the pure theoretical contributions, but all the work that you have done around. So you have done really impressive work around your thesis, also supervising a lot of students and collaborating in a lot of side activities. That is also very interesting during your PhD. So just want to highlight that. And well, so maybe I can just ask a quick question, because you have already discussed a lot of possible extensions and drawbacks, benefits of the different parts. So maybe just one thing that maybe I missed, or maybe it was not discussed in your papers about the last part, since it's what you're more excited about right now, it seems, this unsupervised learning. Okay, so I didn't get if you are exploring or considering somehow transfer or sharing between different categories. So you're learning these category specific key points, right? And of course, within the category, there is the shared model that you're learning. But is there anything across categories that you can, because unsupervised learning, I agree with you, it's a really interesting field to research right now, but also it's hard, right? And if you can transfer or share things that you have learned from one category to another, I don't know if you have explored anything in that direction, or if it's included somehow in the pipeline and I missed it.
Yeah, so it's a very interesting question. We didn't try that. What we thought at some point was to try to learn all the categories in the same model, but somehow doing a classification first, right? Like to say, okay, according to how this shape is more similar to others, classify them in the same category, let's say. But at the end, it's something that we had in mind, but in the end, we didn't try it. It's something that I will try. I would like to try at least in the future. But it's true that some categories share similarities with others, right? For example, in this case, chairs, beds, tables are not that different. So it would be nice to see like how the embedding of the shapes change from one category to the other. But that's something that we didn't explore yet, but it's interesting, yeah.
Well, as you said, all the good research also brings a lot of new questions. So yeah. Obviously, again, you have done a great presentation explaining really clearly a lot of different things. So it's it's understandable. There are a lot of open ideas, right? That's actually great. It's a good result also of the thesis that you open new paths, right? So, well, I think I maybe I can just leave it there with just one question, and we can let your actual supervisors now. We can let them talk a little bit. And congratulations again. No problem.
Thank you, Ana.
Okay, so the real supervisor now. Jose Guerrero, maybe start.
Okay, good afternoon, everybody. Well, first of all, I would like to thank Thierry, Thomas, Mathieu, Christian, and Ana Cris for agreeing to participate in the thesis committee. Thanks. And also in special detail, Christian and Mathieu for your deep reading and your suggestions to improve and clarify the manuscript. Well, in any case, we are here to talk about Clara's work, and the first thing I have to tell you is congratulations, Clara. I am very satisfied with the research work you have done. You have achieved several contributions for better scene analysis, and you have considered the vision-based understanding in 3 levels, and you made brilliant contribution in the 3 levels. No? I must to highlight your contribution in the first level with your operator adapted to equirectangular images, equicoms. I think it's a great contribution, and probably is the best way in the world to extend convolutions and convolution neural networks to panoramic images. Okay, but well, as supervisor, only want to highlight your great enthusiasm with the research work, your capacity to face new problems, even if your knowledge or your training was not the most appropriate. Mm-hmm. Your outstanding social skills to collaborate, to work as a team, to transmit results to others. And finally, your contagious fascination for what has been achieved and your illusion to face what remains to be achieved. Okay, congratulations, Clara.
Thank you, Jose.
For my part, is all. I'm not going to ask you questions. We have already spoke and discussed many times. Mm-hmm. These nearly 4 years. It has been a pleasure to working with you these years, and I wish you the best in your professional career.
Thank you. I say the same. It was a pleasure to work with you.
Thank you. And last but not least, Cédric.
Thank you, Thierry. Thank you, President. So I will say a few words because I think the time is running, and so I cannot keep the floor a lot of times because I think Thomas, I have an open point in a couple of minutes. So first of all, I would like to thank, of course, the committee member, so especially Christian and Mathieu for their great job. It's always difficult to do a report before the defense, and it was really interesting to read it. So thank you guys. I would like also for sure to thank the examiner. It's really important for us to see you, and thank you for being here. Oh, remotely. Okay, so Clara, I don't have any question for sure, but it was a really pleasure for me to work with you, even if honestly we did not have a lot of opportunities to work together at the same place due to crisis and so on. So anyway, but okay, I see that Clara is really autonomous. She's able to find the right people for helping her. So I would like to thanks also to take the opportunity to thanks Ajad. I saw that Ajad is here, and DP also, because they work with you for the last chapter. So, and anyway, Clara is always available to help other PhD students for my team. So thank you, Clara. It's really important for us. I'm sure that you will become a great researcher, and I hope we will still have the opportunity to work together. So thank you. Thank you. Thank you so much.
Thank you, Cedric. Yeah, we will continue collaborating in the distance at least. Yes,
I hope so.
For sure.
Okay, thank you very much. Now I think we should move in the other room, virtual room, and we come back after.
Okay,
so,
thank you.
See you in a few minutes.
You can turn on the camera now so that I can see you, maybe.
Clara, súper bien.
Thank you.
Muy bien, Clara, muy bien. Pero bueno.
Hola, Clara. Muy guay. Te ha quedado genial.
Thank you. It's nice if at least I can see your faces now.
Me encanta el fondo.
Yeah, right. It's super nice. It looks like a fake background, right? But it's not.
Hola.
Yeah, like green screen.
Hola. Gracias. And Tema, you're the next. I don't want to put pressure with these words.
I know. Well, Some of your slides. Make sure to share them with me, please.
Hi, Clara.
Hi. How are you? Amir?
Fine, and you?
Fine. Long time to see you.
Yeah, I'm the next,
Uh-huh, okay.
Week after the next week. In
Okay.
2 weeks, yeah.
Okay. Then I'll be there. Good luck.
Thank you.
Enhorabuena.
Thank you, Jose. I don't know why I can't see everybody, right? I just see like 4 or 5 faces.
Pero me está viendo.
I'm sorry that we will not have a real apero after this, but we will celebrate it when this Corona stuff finishes. Hola Jesús, no te había visto.
Congratulations, Clara.
Thank you.
Enhorabuena. I have to go to a lecture now for a class.
Okay, thanks for attending.
So I know the result. So congratulations again. And I expect to see you soon.
Yeah.
And
Christmas.
of course, celebrating your defense. It was nice.
Okay, thank you, Jesus. Bye.
Bye.
Do you know how long does this usually take? It looks like they forgot about us. $15 minutes.
Clara,
Hi, Patri. How are
¿qué
you?
tal? How are you?
Muy bien. ¿Cuándo
Yo creo-
vienes?
La semana que viene.
Vale, porque a ver si vas a venir cuando ya me he ido.
No, nos vemos la semana que viene. Nada, que te ha salido súper bien, has puesto el listón súper alto, te ha quedado súper bien la historia y todo. La verdad que, joder, felicidades.
Gracias.
Te ha quedado muy, muy bien.
Gracias,
Y nada,
Patri.
ya. Ahora vendrán, te dirán que un excelente y ale.
Jolín. Estaba nerviosa, ¿eh? No, pero genial, ahora vamos, súper feliz. Ya ha pasado.
No, pero al final es tu tema y lo has defendido bien, muy bien.
Gracias, Patri. Qué ganas de que vengas ya por aquí.
Nada, que vaya bien. Cierro aquí, cierro el audio que en silencio.
Vale, ya.
Muy bien.
Hola Clara, enhorabuena.
Gracias, Julia. ¿Qué tal? Estás
Muy
en
bien.
Friburgo, ¿no?
Desde Friburgo.
Muy bien.
Muy bien, muy bien. Te ha quedado genial, lo has hecho súper bien.
Gracias, me alegro que os haya gustado tanto. Me está encantando porque estoy recibiendo por WhatsApp millones de fotos de todo el mundo viéndolo en sus casas, tal, con la cámara.
Sí.
Genial.
Tiene la parte mala y la parte buena también.
Sí,
Seguro que
claro.
se ha unido más gente.
Sí, eso sí. Además, como en Zaragoza están haciendo el streaming en YouTube, eso también ha estado bien.
Hello, Clara.
Hello.
You are coming. Just to be sure that everybody is here.
We are back, more or less.
Yes, more or less.
More or less.
slowly getting back to this other room.
Okay, Anna.
Yeah, I guess being a co-tutel between two universities, the document and everything, it's
Big boring, but anyway, Anna, thank you so much for sharing that.
No, don't worry. So you still had company here, right? You still had public staying with you. You were not alone all this time. Okay.
Christian is here. Thomas, are you here? Thierry?
Yes, I'm here.
Yeah, Thierry, you are here also. So Christian and Mathieu. Mathieu, are you here?
Yeah, as well.
Okay. So maybe Thierry can speak a little bit.
Yes, I speak for 2 minutes, but I was muted my microphone. Sorry. So Clara, the committee has write a report for your talk, and we write that you gave a very clear and very well illustrated presentation of your work, motivating the problem and describing your contributions by focusing on the key ideas and results among many original aspects. Your presentation highlights your knowledge in deep learning, geometry, and computer vision, and your capability of proposing original methods. We ask you many questions on both scientific and technical aspects of your methods and the impact of your work on the field and future works. And you provide detailed answers, showing your extensive understanding, knowledge, and vision about the field. Moreover, we would like to emphasize that on the top quality of your publications on ICRA, IROS, CBPR, Workshop, and ECCV, and the extensive comparisons of your work with state-of-the-art and reproducibility of your works thanks to the code you release. So, and this is a conclusion, for all these reasons, the committee unanimously decided to grant you with the title of Doctor in Computer Science, maybe, yes, of the University of Burundi and Zaragoza. So congratulations.
Thank you.
Congratulations.
So, yeah, thank you very much to all of you for attending today and all the messages that I've been receiving with all the pictures from all of you watching the presentation at home. It was super nice. And I hope that we are able to celebrate it soon, like either in Zaragoza, Legroso, here in Zurich. Right now, I will try to do a small celebration, at least with flatmates and coworkers. But yeah, I hope that we can celebrate it as well with the rest of you soon.
Okay.
Yep.
Thank you.
And goodbye. Thank you very much.
Okay,
Thank
bye. Congratulations.
Bye, everybody.
Congratulations.
Bye.
Bye.
Bye-bye.
Bye. And have a nice day, Thomas.
Christmas.
Congratulations.
Bye-bye.
You did amazing.
Thank you.
Hi, Cedric.
Ah, salut.
Ah,
Hello. Thank you, guys.
See you soon.
Bye.
Bye. Take care.
Bye-bye,
Thanks.
Clara.
See you soon.